Hi, everyone, and welcome back. So today we begin our discussion for Unit 4. So Unit 4 is actually going to be a reversal of pretty much everything that we've learned up to this point. So for the first 3 units, our focus has been on derivatives and analyzing how a given function f of x changes using its first derivative f prime, and then further analysis with the second derivative f double prime and how that influences or has connections with the rate of change given by f prime and then the original function's value and concavity. So we've looked at all those different connections and the relationships between f prime, and f double prime, and now we're going to learn how we go backwards, because in pretty much everything in math, we learn how to do it in one direction, and then we analyze and realize that we can do it in the reverse direction, and that typically reveals some other hidden patterns and applications, and that's really the focus of Unit 4. So up to this point, we've been working within the realm of differential calculus. We've been using differentiation to find derivatives. Today, we're going to do antidifferentiation, or use antidifferentiation to find antiderivatives. So a lot of what we've done up to this point, we're going to do just in backwards. We're going to do it in the reverse order. So for example, I have 6 functions here. Each of them are identified or named as f prime, which means each of these represent the derivative or the rate of change of some other original function. So if we really think hard, you guys could probably piece together what kind of function we could have started with and ended up with these as their derivatives. For example, the first one, pretty easy. So we know from past discussions that if the original f of x function is a polynomial, then its derivative is also a polynomial. So by that logic, it follows if the derivative is a polynomial, its original function, or the antiderivative, is also a polynomial function. So that means it's kind of just the reversal of our power rule. So 2x is something that we have written down as f prime for lots of different functions, because that stems from the original function x squared. If I had started with f of x equals x squared and used the power rule, the 2 comes down, the new power is 1, so we would end up with f prime of x equals 2x. So that one's pretty simple. Next one, if I ended up with f prime of x equals 6x squared, well, x squared is the derivative of x cubed, so there had to have been some kind of power rule, and the old power was 3, so we could think of this as 2 times 3x squared. So this 3 really kind of just goes back up top and becomes the old exponent. So in this case, we could have started with the function 2x cubed. And the best part about this, well, we're doing this trial and error process right now. If you're not sure if your guess is the correct answer, then we could always just take the derivative and reverse or go in the normal direction that we always have. So that's the best part about this. And again, this isn't the first time that you guys have seen this relationship with going in one order and another. In elementary school, you first learned how to multiply, then you learned how to divide. In algebra, you learned how to multiply polynomials. Then you learned how to factor polynomials. They're all connected. They're all the same thing, but we're just doing it in different orders. And while we're doing it in a different order, we reveal some hidden patterns and relationships that may be of use to us. Next one, f prime equals cosine. Well, that is one of our known derivative rules. That is the result if I started with sine of x. So that is our original function. Okay, now a little bit deeper. This one's a little trickier. There are 2 terms, which means if there are 2 terms, then I could have started with 2 terms in the original function. So e to the x is the derivative of itself. So I know that just reverts right back to the same thing, e to the x. 3 is a constant, and I know that that is the derivative of a linear function. So we must have had the linear term negative 3x. So pretty straightforward. Now this one's a little trickier. This one is a rational function that we ended up with. But if you think carefully, go back and dig through your memories for all the derivative rules that we have looked at so far. Hopefully you guys realize that this fits the format of u prime over 1 plus u squared, and that is the derivative rule for arctangent of u, and in this case, u would simply be x. So this would be arctangent of x. And then the last one, this is definitely the trickiest of all of them. It's a rational function. You guys would not be able to just look at this and realize that if we had started with a quotient rule, what the four things would be and put it all together, and you wouldn't be able to look at a derivative that was the result from a quotient rule and revert back to the original quotient. There's just too many parts involved with that. So keep that in mind as we go through some of these problems today. There's not really a reversal for the quotient rule or even the product rule because there's so many moving parts that can be distributed and combined with like terms. It would be impossible for us to sort all that out for right now. So keeping that in mind, the more basic rules, hopefully you guys can look at this and realize or recognize that the numerator in this case is actually the derivative of the denominator, or this fits to the format of u prime over u, which is the derivative of natural log of u. So this would actually be natural log of 2 minus 5x. Now, without getting too far ahead of myself, we have to do something special here because this derivative function has a domain that x can equal anything that is not 2/5. If x equals 2/5, then the denominator equals 0, and it's undefined. But any other value of x, we can simplify, or we can substitute into this f prime and get a value. Which means if that's the domain for the derivative, we have to be able to navigate back to a function with that same domain. Because if I can plug every other value of x in here, that means that f prime of those values represents a slope on a point on the original at every value of x except for 2/5. So we have to make sure that the original function matches that domain. Normally, natural log of u, this u has to be strictly greater than 0 because you can't take a logarithm of a negative value or 0. Well, still can't equal 2/5, so that part still matches because that would produce 0. But if I don't have those absolute value bars in there, then if I plugged in x equals 1, it would produce a negative argument, so we'd have to remove that value as well. But by putting these absolute value bars around it, it allows us to use every other value of x except for the one that makes the argument 0. So this is going to be a special relationship. We're going to see this rule here pop up in a minute on the list. When we go backwards with this natural log, the natural log always has to have absolute value bars around that u. It's a special relationship. Again, when we go backwards, sometimes we reveal extra little hidden things, and that's what's going on here. So going in that reverse order tells us that we have to have those absolute value bars on there. All right, now, what we just did, all 6 of those problems, we found something called the antiderivative of the derivative functions that we started with. So again, derivative is when we move from f to f prime, but if I start with the function and I go backwards to the function that came before, that is referred to as the antiderivative. So that's the name of the thing or the process, antidifferentiation, but notationally, we still have our primes notation and our dy dx stuff. So another way of expressing that we went backwards is changing the name of the function. So if f prime is the name of the function to start, when I go backwards, we use just regular f of x. Now, another way of doing that, so there's another notation, a couple different ways that you will see this being done. Sometimes we will use a different name. So again, if I start with f prime and I go backwards, then we call it f. But there will be some situations where I actually just start with f of x as the function that I'm beginning with. So if I want to go back before that guy, there is no way for us to strip away a prime symbol if it doesn't start with 1. So the adopted notation for this is we switch from lowercase f to capital F. That is an indication that we went backwards from our lowercase f of x function. So it's another notation way of representing that we went in that reverse order. So definition here, a function capital F is an antiderivative of little f on an interval if the derivative of capital F is equal to little f. So again, it's just another way of expressing that relationship. So we can call this guy the antiderivative of little f of x if I take the derivative of this equation and it spits me back out where I started. Okay? So just some of the notation stuff that we have to get kind of out of the way. Now, one big important question that we have to ask ourselves: how many different functions f of x have a derivative of f prime of x equals 3x squared? Well, if we think about this just the way that we just did before, if f prime is 3x squared, and we kind of think back through the rules that we know, it's pretty obvious that this one was a power rule, and hopefully most of you guys can figure out that when I go backwards, this would just revert back to f of x equals x cubed. However, that is not the only function whose derivative is 3x squared. So if we think back into all the different things that we've talked about so far, about how the derivative function represents the rate of change of the original function and what things make contributions to that rate of change, hopefully you guys remember something that we talked about way back towards the beginning of the course. And that is the fact that a constant term, adding a number onto another quantity, just adding that number, does not actually affect the rate of change of this other quantity. If I had x cubed plus some number, when I go to take the derivative of that, it doesn't actually matter what this number is. It could be a positive, it could be a negative. The idea is every constant's derivative is 0. So the x cubed term will definitely turn into 3x squared every time, and the plus c will always just disappear. So what that means for us is that when we start with a derivative function and we use this antidifferentiation process, we aren't just finding one antiderivative. There is an infinite number of possible solutions, and they are all represented by this guy, that plus c. So the way we describe this is when we find an antiderivative of some function, we're actually picking out of a family of antiderivatives. So that's what I mean when I say that there's an infinite number of possible functions that all have the same derivative. Or visually, again, if my original function, or let's name it f prime of x, is equal to 3x squared, then, oh, you know what, it's not going to let me do that. So ignore the notation for right now. There is my original function, f of x equals 3x squared. We just talked that its antiderivative is x cubed. But again, that is just one of them. So again, what this relationship is saying is that the blue graph represents the rate of change of the green graph. And we can see that. The green graph is always increasing except for 0, where it goes flat for a second, so that the slope is 0. And if you notice, the blue graph only uses positive y values except at x equals 0. The green graph is very steep on the left side, and then it flattens out towards the middle, and then it gets steep again. That would mean that the blue graph's y values are very large positives on the left. They get smaller and smaller, approach 0 at x equals 0, but then they get bigger and bigger positive values again. So if all I do is add a constant to that green function's or green graph's function, all it did was shift that graph up 2 units. It did not impact the slope whatsoever, because I didn't just add 2 to some of the y values to change the spacing, I added it to all of the old y values. So what we see is it doesn't really matter what that function's constant value is. As I change that c value, all it does is shift up and down, and that's not anything new. You guys have seen that before in the past with function transformations. What's new now, though, is the idea that because it's just a vertical shift up and down, it has no impact on the rate of change of the function, or the slope. That is why all of these infinite number of functions, derivatives, all send us right back to the same place, 3x squared. So, because of that, that constant value that separates the different antiderivatives, special names, vocab, that is referred to as our constant of integration, okay? We'll get to that word integration here in a second. So the family of functions represented by G, it's referred to as the general antiderivative. So we say general because we're not picking out a specific value of c. When we use just kind of a placeholder, that variable c, it represents all of the different possible values. So it really is representing the entire family of antiderivatives. So a differential equation in x and y variables, it's an equation that involves x, y, and the derivatives of y. We've worked with these in the past. We just haven't specifically used that name all the time. But a differential equation, it would be something like y prime equals 3x squared. Or we could also think of that in the other notation as f prime of x equals 3x squared. Same idea. But when we find the solution to that equation, or the general antiderivative, and we leave c in the equation, we refer to that as a general solution. So it's just another way of expressing that when we go backwards and we don't pick out a specific c value, we are leaving it in general terms rather than finding one particular antiderivative. So this entire process is referred to as indefinite integration. So when we solve a differential equation of the form dy dx equals f of x, we usually want to rewrite the equation in a more convenient form, where we separate the dy and dx stuff, and so we get the change in y, or the derivative of y, is equal to f of x times that dx quantity. So this is a little bit more beyond just the nuts and bolts. There's some heavy conceptual stuff that's going on here, but if you think about it, we want all the y stuff on one side, all the x stuff on another, so that if I wanted to go backwards, we have all our variables separated where they need to be. So these parts have some special names to them, and it's a bit of notation that we really have to get used to. So the process, again, thinking back to the beginning of the year, differentiation was the verb in the math language, and then the derivative was the noun, the thing that we got. We have that same kind of idea here. We can call the process, or the verb, antidifferentiation, or indefinite integration. They both mean the same thing. The indefinite integration is the one that we're going to use more often. Okay, so integration is another name for the backwards process. We're starting with an antiderivative, or excuse me, a derivative function, and working our way back to the original. So indefinite refers to the part, or the idea that we end up with this plus c. So we are not finding the particular solution. We're finding the family of antiderivatives. So notation-wise, all this stuff over here. So essentially, we're going to use this fancy new symbol. And then this guy wasn't labeled. So that's like an elongated S symbol. It is referred to as the integral. Okay. In particular, this is an indefinite integral, because our job is just to go backwards and find the equation of that antiderivative. There's a second type of integration called definite integration, which we will get to later on in this unit, but that is used for a specific goal that is different than just being able to find this antiderivative. It involves that, but there's an extra application that we have to worry about. So we have the integral, and then inside of this integral, there's an argument. So think of this as like natural log. Natural log has an argument. Radical functions have arguments. Sine functions, every trig function has an argument. That argument is something that is attached to that notation. Without that argument, it means nothing. Same thing. If I just wrote an integral symbol, this is not like a mathematical operator that can mean something without what it's attached to. So we have to have something inside of this guy. The stuff that is inside of that guy is referred to as the integrand. So all of this stuff, the function, along with this dx quantity, is referred to as the integrand, the inside or the argument of that integral. So inside that integrand is going to be the function, the actual expression that we are working backwards from, and then this extra little quantity of dx. So this guy is referred to as the variable of integration. So in terms of our derivative stuff, think back to when we would use the d dx notation. So the idea there was x was the variable that was kind of driving all of this. We wanted to look and see how a particular pattern for y changed as x changed. So this was the derivative or the variable we would take the derivative with respect to. Same idea, but now we're going backwards. So now we want to go backwards and look at how the original function would operate with respect to x. When we write these integrals, this guy has to be in there. So just like a square root means nothing without the inside stuff, an integral means nothing without that dx quantity. It must be in there. So notationally, when you guys are practicing these problems on your own, you need to make sure that you're always including that dx. So for right now, we're only ever going to be integrating with respect to x. Eventually, we're going to look at some problems where we may be integrating with respect to t because the input of our function is t. But there are other times where we may write integrals that have extra variables in them. And so we want to make sure that we know what variable is controlling everything and how we apply the different antiderivative rules. So that dx is actually a pretty important piece. So we will do our special math. We will learn how to do these different rules. And then that spits out our antiderivative, capital F of x. And notice it's capital F here because we started with lowercase f. So when I go back, we have to denote that. And then we always have to make sure that we have this constant of integration, okay? So again, the idea there is we have a general solution. We don't know specific information about which one of the original functions we are picking out of. In order to do that, we would need to know some extra information about the original function. So that's the general process, okay? So now what we're going to do, rather than when we learned our derivatives, we learned the rules in batches. But for integrals, you guys already know all of them because they really are the exact same derivative rules, just applied in reverse with a couple of exceptions. But majority of these are identical to what you guys already know. For example, derivative of a constant is 0. So the integral of a 0 is just some constant. Derivative of a number times x is just that number, that slope out in front. Well, the integral of just a number is that number times x plus c. If you look up and down here, all of these guys end up with a plus c at the end of them, except for these two, and that's because these two are demonstrating a property and rather than an actual rule. So for these two, this is actually the same as these derivative rules. So a number times a function, its derivative is that same number times the derivative of the function. So this is that scalar multiple rule. And then the sum and difference rule, remember, if we have multiple terms, we take the derivative of each independently. That is the same for integrals. We can actually take the integral of a sum or a difference and break it up and integrate each individual term. So it operates just like the same process that we used for derivatives. Now for the power rule, the old way was the old exponent comes down to multiply out in front, and then we subtract 1 to get the new power. So we're literally going to do the opposite of everything I just said. So now when I integrate x to the n power, we will add 1 to the old exponent to get the new one, and then divide by that new power. So not only did the order reverse, but the operations did as well. So if you think back to problems that we've already done, earlier we found the antiderivative of 3x squared, but if I wrote out that notation correctly, it would be the integral of 3x squared dx. So I'm going to add 1 to the old power, that becomes cubed, and divide by that new power. So the 3's cancel, and so we're left with just x cubed, and then we have our constant of integration plus c. All of these other rules are almost identical. The only exception here are the trig rules and their signs. So this is a little tricky. So sine turns into cosine, cosine turns back into sine. But then for this guy, the derivative of cosine was negative sine. But if I have a negative inside of an integral, this property up above, this guy says that I can move that constant out. So because of that, we don't really have rules that start with things that are negative. Instead, they turn into negative things. So it's a little tricky, the order there, but basically the sign relationship here still exists. So cosine would turn into the opposite of sine, so sine turns into the opposite of cosine. Okay, so basically the old way was if the function starts with the c, its derivative is negative. In this case, if the antiderivative starts with the c, the result is negative. So it still has that same kind of relationship. All these other guys are just if I start with the derivative rule, we revert back to that original function. Derivative of tangent is secant squared. So if I start with secant squared, it goes back into tangent. Same is true for our other transcendental functions, our e to the x's, our non-base e exponential functions. So here, again, everything is kind of opposite. So if it was base a to the x, its derivative is still that exponential, but you multiply by natural log of the base. Now we have to divide by natural log of that base because it's in the reverse order. Natural log of x turns into 1 over x, while 1 over x now turns into natural log. Notice these absolute value bars. I told you guys that earlier. That has to do with maintaining that same domain as the original function that we were integrating. Now, one other thing to point out here. None of these integration rules right now have u's in them. Remember, we learned these basic form of these derivative rules, and then we also learned the chain rule version of these. Well, chain rule with integration requires a special process, which we will get to later on towards the end of Unit 4, but that is coming. We do learn how to take the antiderivative of those. But for now, let's just try some out. So again, I'm going to go through these. You guys keep in mind, you can look back up to the top of the page as we are going through these. So the first one, this is here on purpose. It's the easiest in the entire notes packet, but it's also the one that students forget most often and struggle with. There is no function written in here, and that's because it really is a constant function, and the only constant I can multiply by and not have to brag about it is 1. So this is really a function, a constant function of 1 times dx. So the rule above says that the integral of any constant is that constant times x. So this is really 1x, but then we have to write plus c. So that is our answer. Now, notationally, what you guys are expected to be writing here, you do need to keep in mind, this notation, this process is very similar to had I written this out on your paper. If I asked you to do this and evaluate, you could just say that this is equal to 1. I'm telling you to take the derivative of a function. This is saying find the antiderivative of 1 with respect to x. So we don't have to give this a name of capital F or f of x, whatever it is. We don't have to use function notation unless it actually says, here is a function f prime of x, find f of x. If we're given function notation, then we would want to represent our answer in that way as well. All right, now the next one. This is a sum of terms. So if we follow the rules to the letter, then I can break this apart and write it as integral of x dx plus the integral of 2 dx. Now, you're not going to do this every time. I'm not even going to do it on the next problem because it doesn't need to be done that way. But this is just to demonstrate that we can really integrate or find the antiderivative of each individual term, just like we would find the derivative of each individual term. But when you break this apart, because there will be times where it's absolutely necessary to rewrite as separate integrals. But when we do that, notice that each term gets that dx. This is like us distributing dx to both pieces and then breaking it apart. Again, you can't do math, you can't do this calculus without that dx quantity in there. So now we just do the power rule. So integral of x to the first, again, it's everything in the opposite order and operation. So I'm going to find the new exponent first by adding 1, and then I divide by that new power. So I get x squared over 2, and then plus 2x. And again, even this constant rule, you're still technically doing the power rule. This is really 2x to the 0, so this becomes 2x to the first over 1, but those 1s are unnecessary. And then we can't forget our constant of integration. Always have that plus c. If you're supposed to have plus c and you don't, that will cost you on assessment. So make sure that you guys have that in there. It is extremely important. All right, now the next one, again, I'm not going to rewrite every single term every time. I'm going to put little lines here to help your brain separate and realize that this is just 3 problems put together. So 3x to the 4th, that would become 3x to the 5th divided by 5. If the variable already has a coefficient, then it just comes along for the ride as well. And it just interacts with that new value in the denominator, just like it would with anything else. Then negative 5x squared will turn into negative 5x cubed over 3. And then plus, this will turn into x squared over 2. And again, we can't forget our plus c. All right, now just one quick note about the constant of integration. If we were to follow the rules to the letter of our, there's a little typo. If we were to follow the rules for integration to the letter, technically speaking, I should be pulling this constant multiple out in front. So we get 3 times the integral of x, because technically the power rule wants it to be x to the n power only inside. It doesn't need to be that way, but if we follow the rules exactly, then that would result in 3 coming along times x squared. This is supposed to say over 2, not over x. Sorry about that. X squared over 2 plus c. But then when I distribute, this becomes 3 halves x squared plus 3 times whatever this constant is. But if you think about it, c represents all possible constants that can be added on there. Well, if you take 3 times any number, you're just going to get some other number. So we don't have to go through this process when we do these problems. It's totally acceptable for you to ignore the c until the very end of the problem, do all the calculus with the other algebraic terms or whatever functions we have, and then at the very end, we're just going to slap on a plus c. So that c kind of is all-encompassing. It's going to represent all of the possible values that we can add on there, including negative. So even though it says plus c, it doesn't necessarily have to be a positive number, and we'll see that with a couple examples here in a little bit. All right, so just like with derivatives, sometimes to fit to the form of the rule that we want to follow, we have to rewrite sometimes. So if you think about it, anytime that we started with a negative exponent with derivatives, we would end up with a negative exponent in the answer, and then we'd rewrite it so that there was no longer a negative exponent. So now think of these as the results of those. So there's always going to be some rewriting involved, or not always, most of the time with the harder problems, there will be some rewriting involved. But that's just to fit to the form of the rule that we need. So for example, integral of 1 over x cubed dx, that doesn't fit the rule of anything the way that it's written right now, but we could simply rewrite this as x to the negative 3rd dx. Now it fits to the power rule, and now we can use the power rule. Now remember, we're adding, so this is a little trickier with these negative exponents. So x to the negative 3rd, if I add 1, will now become x to the negative 2nd, divided by that new power, plus c. But again, we don't want to leave the negative exponents in there. So the negative sign I can actually move to the top with the 1 that's left there, but this guy, remember, needs to go to the bottom. So we get negative 1 over 2x squared plus c. And again, a quick rewrite, if this was the function that I started with, you wouldn't want it in this form anyways. You would leave the 2 down there, so we'd have negative 1/2 times x to the negative 2nd. If I take the derivative of that, negatives cancel, 1/2 times 2 cancels, and subtract 1 gives me negative 3 as the new power. So again, that's always a quick, easy way. We can always check ourselves simply by taking the derivative of this result and seeing if it reverts right back to where we started. All right, 1 over the square root of x. Again, I'm going to do this a slightly different way. You haven't seen me do this yet, but this coefficient can really come out in front. So if I just want to get the extra numbers out of the way, you're always allowed to move it outside of the integral, but that's only for constant multiples or coefficients. You cannot move functions of x outside of the integral, otherwise it's meaningless. So that comes out, but then this square root of x is in the denominator, so I can actually rewrite that as negative, or x to the negative 1/2 power. Now, if I execute the power rule, again, the 1/2 just comes along, times, I'm going to add 1 to the old power, so that becomes positive 1/2, and then I'm going to divide by that new power. So with fractional exponents, that's always tricky because when you go to divide by the new power, it's a fraction. But remember that dividing by a fraction is like multiplying by its reciprocal. So this is really 1/2 times x to the 1/2 times the reciprocal of 1/2, or 2. 1/2 times 2 would then cancel each other out. So we're left with x to the 1/2 plus c as our final answer. Which, if you really look at it again and think about it, that kind of, or should make sense, because this is one of the most common derivatives that we found. We've taken the derivative of square root of x a bunch of times now, and it's always resulted in 1/2 times the square root of x. So again, lots of commonalities between what we've done and what we're doing. So speaking of which, square root of x is now what I'm going to start with. So again, radicals we like to rewrite as fractional exponents, so we can use our power rule. So x to the 1/2, if I add 1, will become x to the 3/2. Again, 1/2 plus 1 is like 2/2, so we get 3/2. But we're dividing by that new power, which is always going to result in us multiplying by the reciprocal. So we get 2/3 x to the 3/2 plus c. Now, for trig, there's always going to be some special tricks that we can do with this. Mainly, if I start with sines and cosines, typically if it doesn't work out the way it needs to, or with what it has currently, an easy trick is trying to replace with the reciprocal functions or tangents. For example, now this one we got to get pretty creative with. I'm actually going to separate this guy. I'm going to do it in a couple stages, so just so not to confuse anybody. Remember that cosine squared is really this guy, cosine of x, quantity squared, which means it's just 2 cosines being multiplied, which I could also think of this as the integral of sine of x over cosine of x times the fraction 1 over cosine of x. Whoops, forgot my dx. So if that's the case, sine over cosine is the same thing as tangent x. 1 over cosine is the same thing as secant x. The order of these guys does not matter because it's multiplication, so I really could just think of this the other order, which is more common, secant x, tangent x. That is the derivative rule for secant, so that is our antiderivative, secant of x plus c. All right, now this next one, this looks like a product. We do not know a product rule yet for integration. So if it starts as a product, your job is to actually multiply. So we need to rewrite this, and the simplest way to make this easier would be to distribute. Again, just like with derivatives, if you can do some algebra first to make things easier, do it. So this really becomes 6t squared, or excuse me, 6t cubed minus 18t squared plus 2t dt. Now, one thing I do want to point out, notice that there are parentheses around this because there are more than one term being added or subtracted. Anytime that your integrand, your function that you are integrating, has more than one term, it needs to have parentheses and then the dt or the dx on the outside. So please be aware of that. Also, notice that this is a different input variable. This is a function of t instead of x. But because this variable and these variables match up, we just do things like normal. Okay? So, executing the power rule, this would become 6t to the 4th over 4. We'll simplify in a second. Minus 18t cubed over 3 plus 2t squared over 2 plus c. And then we can reduce all of these guys. So we'd really have 3/2 t to the 4th minus 6t cubed plus t squared plus c. All right, this next one, it's pretty straightforward. There's actually no rewriting needed to do to this one. Everything's there that I need. So t squared will just simply become t cubed over 3. And then again, that constant, it just becomes 1 times the variable of our input, so plus t and then plus c. So they're not all super crazy or require extra stuff. Some of them are straightforward. All right, now the next one. I've got a quotient. The only quotients that you know for derivative rules are the inverse trig, Those functions have derivatives that end up being fractions, and then our natural log rules. Anything besides that, you guys don't know rules for it. So there's, again, like we talked about earlier, there's no way for us to look at a function that ends up as a fraction and know what quotient rule problem we started with. It's impossible because of all the pieces that can be manipulated in those problems. So that should be something to look out for, which means there's algebra to be done to this. So just like when we had problems like this that you wanted to take the derivative of to avoid quotient rule, we want to do that here as well. This is a split and reduce problem. So this will actually become x cubed divided by x squared, or x, plus 3 divided by x squared, which I can rewrite as 3x to the negative second dx. Now this guy can be integrated using the power rule. X will become x squared over 2, plus this guy will become 3x to the negative first divided by negative 1. Or the better way to write that would be minus 3 over x to the first. And then when we're done, remember we can add that plus c on at the end. All right, now, next one, again, starts off as a product. We can't do that, so we have to actually carry out the multiplication. In doing that, that radical cube root of x is really x to the 1/3. So x to the 1/3 times x to the first, or, whoops, got ahead of myself, x to the 3/3 power is going to combine to be x to the 4/3. Then minus 4x to the 1/3. Again, I haven't done any calculus yet. That was all to make it easier for us. Now we can apply the power rule. So adding 1 to 4/3 would be adding 3/3 to it. So we get x to the 7/3 divided by 7/3. And again, we'll clean that up in a second. Minus 4x to the 4/3 power now, divided by that new power of 4/3. Plus c, and again, we'll clean this up. So multiplying by the reciprocal, that would give us 3/7 x to the 7/3. For the first guy. But for the second one, when I'm multiplying by that reciprocal, I'm multiplying by 3 over 4. So the 4's are actually going to cancel. So we end up with minus 3x to the 4/3 plus c. All right, and our very last one. So secant squared, again, we have multiple terms, so we're going to take the antiderivative of each. Secant squared, that is the derivative of tangent. So this just goes back to being tangent of theta. Notice a different input variable. All of these guys are using that same thing, so we treat it like normal. 2 over theta, though, that would be like pulling the 2 out, and we end up with 1 over theta d theta. And again, the thetas might be throwing you off, so maybe if you guys saw it as 1 over x times dx, or also we can write that as dx over x. All of these are telling you to use the natural log rule. So this is actually going to become plus 2 times the natural log of theta. But remember, when we integrate and end up with the natural log, you must always have absolute value bars. Okay, the exception to that would be if the inside is something that is always positive already, like x squared or e to the x. That would be the only exception, okay? So we need the absolute value bars there in this case. Now, cosecant squared theta, that was the derivative of cotangent, but it was supposed to be negative. So again, it's really just saying that there has to be a sign change. So for the derivative, if I started with a positive, I ended with a negative. Same thing is true for the integral. I'm starting with a positive, so I got to switch signs. So this will be minus cotangent of theta plus c. And that's it. So all the practice problems that you guys are going to take a look at later on with this section, it's really just different variations of these. So again, always be creative in thinking of ways to do some algebra or rewrite beforehand so that it fits to one of the known rules from that list. All right, now we're going to take a look at something called initial conditions and particular solutions. So remember that there's always going to be an infinite number of antiderivatives for any given function. All it really depends on is which value of c we choose. And which one we need to choose depends on a particular piece of information that we know about one of the original functions that ended up with that particular derivative. So to do this, we need extra information. So that extra information we refer to as our initial condition. Essentially, when we look at all the different family of possible values, think back to this example from earlier, we basically need to know at least one point that the original function or the green graph passes through. If I know one point that it passes through, then I can actually use that to solve for a particular value of c that would create that particular antiderivative. So that's the difference between general solutions or general antiderivatives and particular solutions. So it's essentially the exact same process, but at the end we're going to solve for c using a point that we know it passes through. For example, the solution to the differential equation f prime of x equals 3x squared plus 1 has only one curve passing through the point 2, 4. So if I think about that, so 3x squared plus 1. So it's actually pretty simple or similar to this example. So that guy is the derivative to some original function. So what we want to figure out is, out of its antiderivatives, which one passes through the point 2, 4. Okay? So we want to make sure that the antiderivative passes through that particular point. All right, so let's do some calculus. So notationally, what I'm going to do is I'm going to take f prime and integrate. So I need to create an integral here. This is the first one we've written out from scratch. So I'm going to take that function and integrate, put it inside the integral as the integrand. So now I'm going to do my calculus and reverse everything. So 3x squared becomes 3x cubed over 3. You guys are going to get to a point where you look at this and realize the 3's will reduce out and you don't even need to write them anymore. That's how good at this you're going to end up being. And then plus x, and then again, plus c. It always has to start with plus c, whether we have particular or initial conditions or not. So now, because this guy started with a name, I can name this function. This is our original function f of x, and it is equal to x cubed plus x plus c. But again, this represents a family of all possible values. So x cubed plus x, plus c. So I don't know what is the correct value of c to make it pass through that point. Okay, there you can see it just went by that point. So it's somewhere in this range. Now you're not always going to have the graph to help you do this, but we can see here that it looks like -6 is the correct value for c to make it pass through that point. But that's what we're going to do algebraically. Our job is to take this extra piece of information, our initial condition, and solve for c so we know exactly which particular solution we are searching for. So to do that, 2 is our x, 4 is our y, so we're just going to substitute in for x and f of x, and then solve for c. So that looks like this. 4 is our output when x equals 2. So we're going to substitute 2 in for x, and then solve for c. So 2 cubed is 8, 8 plus 2 is 10, so 4 equals 10 plus c, and when I subtract 10 from both sides, we get -6 equals c. And that is our particular, that is our particular value for c, but then we want to actually write out that final answer. So what we know is that the exact equation of x cubed plus x minus 6 will pass through the point 2, 4 and have a derivative of 3x squared plus 1. We want both of those conditions to be true. And that's it. That's all we have to do to find particular solutions. So it's still the same antiderivative process, but then we take that extra point and locate an exact value. Now, the really fun ones, we can actually start with a second derivative and do this process to go all the way back to the first derivative. For example, if I know the second derivative of f is equal to sine of x plus 2, we want to find the particular solution for f of x that satisfies both of these values. So we're going to start by integrating f double prime. So again, if you think about it, if I'm going backwards, if I start with f double prime, then I'll go back to f prime and then go back to f. So let's do that. So I'm going to integrate sine of x plus 2 dx. The integral of sine is cosine, but because the result was cosine, we had to switch signs. So negative cosine plus 2x plus c. So again, this was f double prime, so this guy is f prime. So f prime of x is negative cosine of x plus 2x plus c, and they tell us a particular piece of information about the equation f prime, that when x is 0, the output is 3. So we can solve for this c value. So 3 would equal negative cosine of 0 plus 2 times 0 plus c. Well, cosine of 0 is 1, so this becomes negative 1. That becomes 0 plus c. So when I add 1 to both sides, we get c equals 4. So that gives me the particular solution for f prime. So we have negative cosine of x plus 2x plus 4. But now we're going to repeat that same process over again and integrate f prime to go back to f of x. So we would set up our integral and integrate. The integral of cosine is sine, but because it's already negative, it will stay negative. 2x would turn into 2x squared over 2, or x squared. And then 4 would turn into 4x. But again, don't forget about the plus c. So that is our original general solution, negative sine of x plus all this stuff. But they give us a second initial condition for f of x. So when f is pi, the output is 3. So, whoops. So we're going to use that one and solve for c one more time. So it's a very similar process, just with a different set of functions. So negative sine of pi plus pi squared plus 4 pi plus c. So this one's not going to be a nice number because of the pi's involved. But sine of pi is 0, so at least that guy drops out. So we're left with 3 equals pi squared plus 4 pi plus c. So to solve for c, I actually have to subtract both of these guys. So we just end up getting 3 minus pi squared minus 4 pi equals c. Like I said, that's not a pretty value for this c, but to really write out the particular solution, we have to rewrite this f of x with that guy in there. So we would end up with f of x equals negative sine of x plus x squared plus 4x plus this whole thing. So sometimes you may see constants that are ugly like this guy, and sometimes you'll see parentheses put around them just to acknowledge the fact that that whole thing is the value that you solve for c. Just know that's not necessary. You can put those parentheses in there or not. It really doesn't do anything because grouping those doesn't change their value, okay? But that is it. So we can do this, and theoretically, as long as I have the initial conditions I need to know, there's no limit on how many times we can do this process of going backwards to find more and more particular solutions. All right, so our last topic here is looking at how we can take all this integration stuff and particular solutions and apply it to the real world. So we're going to revisit something that we haven't talked about in a while. These are our vertical motion problems. This is a really easy way to see the application of integration. So if you remember, when we first talked about vertical motion, there was a format, a general equation for position functions for vertical motion. Now, I'm sure you guys, because you're all great students, have that thing committed to memory still and can recite it and write this out perfectly. But because of the power of integration, let's say that you weren't that awesome and you forgot it. You can now recreate it very easily as long as you remember one thing, and that is the acceleration due to gravity on Earth in terms of feet per second is always negative 32 feet per second squared. If I remember that and I know how to do integration, then we can actually work our way back to the position function doing the exact same process we just did. Because if a ball is thrown upward with an initial velocity of 64 feet per second, that's like saying v of 0 equals 64. And if it's launched from an initial height of 80 feet, that's like saying s of 0 equals 80. These are initial conditions, just like the previous problem. So to do this, all I have to do is exactly what we just did. I'm going to start by integrating. Man, those integrals look really bad. There we go, a little better. I'm going to start by integrating my acceleration function, negative 32 dt. Again, our PVA, we write it in that order because when I go forward through derivatives, it goes in that order. But I can also reverse it now through integration. When I go backwards, it goes from acceleration to velocity to position. So this will become negative 32t plus c. So now this is the velocity equation. V of t equals negative 32t plus c. So I can use my first initial condition. That would give me 64 equals negative 32, oops, don't need t because 0 is going in there, times 0 plus c. Or because that's a 0 value, my c is just 64. So my particular solution for velocity is negative 32t plus 64. Notice how that initial, because it's initial and t equals 0, that initial velocity just ends up being this constant. Now I can integrate. So if I integrate the new velocity function with respect to time again, that would turn into negative 32t squared over 2 plus 64t plus c. But again, now I can use this initial condition. So if this is my position function, 80 needs to be equal to half of negative 32 is just negative 16, oops, times 0 instead of t, 0 squared, plus 64 times 0 plus c. But just like with the last one, these terms cancel out because of the 0, and we're left with our c value just equaling this initial condition. So that creates our position function. Negative 16t squared plus 64t plus 80. Or if you do remember the formula, it was 1/2 times my acceleration due to gravity, t squared, plus v naught t plus s naught. That formula was generated by doing integration, starting with acceleration and going back through using these initial conditions. So that is our position function. Now we can use it and answer all those same questions that we wanted to before. That's really the only part that requires the integration. Now I have all three functions, and I can answer pretty much anything. So the next one wants to know, when does the ball hit the ground? Well, the ball hitting the ground is like saying, where is position equal to 0? So I'm just going to set this guy equal to 0, factor and solve. So looking at this, there's a GCF. All three coefficients have a factor of 16. I'm going to pull out negative 16, though, just to make it easier. So I get minus 4t minus 5. We can divide by negative 16 to get rid of that, so it's easier. And that factors to give me t minus 5 times t plus 1, or t equals 5 and negative 1. But just remember, there are sometimes extraneous solutions. So the function equals 0 at negative 1 and 5, but the only one that matters in real world is 5 seconds after this ball is thrown upwards. Okay, then we could answer after how many seconds after the launch, doesn't really need that after again, is the ball back at its initial height? Well, its initial height was s equals 80. Oops, I don't know why I wrote it that way, sorry. Was s of t equals 80. So it's just like the previous problem, we're just setting it equal to a different value and solving. So 80 equals the position function. And this time around, instead of dividing out a GCF right away, there's a common term on both sides which we can cancel out. It's like subtracting 80 from both sides. So while I'm rewriting it for that, I'm going to go ahead and pull out this GCF again. And this time, because it's only two terms left, we can actually pull out a negative 16t. That would leave me with 1t minus 4. So now my solutions become 0 and 4. Well, the 0 we already knew about because that was the initial height. So that one makes sense. 4 is the one that we are looking for now. It would take 4 seconds to get back to that initial height on the way down. So at 0 and then 4 seconds later. All right, let's take a look at one more PVA problem. Now for this one, this is going to be horizontal motion. Okay, so we're talking about a particle starting at the origin and it moves along the x-axis such that its velocity is modeled by the equation v of t equals 6t squared minus 30t plus 24, where t is in seconds and v of t is meters per second. Now, one important piece in here that is kind of subtle and may have been overlooked is that it tells us the particle starts at the origin. So anytime that we talk about where something begins, it's some kind of initial condition. So that is like giving an ordered pair for position that when t equals 0, its position is 0. That's what it means by origin. That is like saying x equals 0. So this is an initial condition for our position function. Okay? Now, for the first question here, it asks, how is the velocity changing at any time t? Well, that's just a test of how well you know these PVA problems. Remember, when I talk about change, that's talking about moving forward in function order and finding a derivative. The change in velocity is the same thing as saying acceleration. So I need to take the derivative of this guy. So when I do that, I get the function 12t minus 30. So this function would tell me how the velocity is changing at any time t. Is it increasing or decreasing? All right, second part. We want to know what is the particle's speed at 3 seconds. Remember that speed is the absolute value of velocity. Velocity has a magnitude and direction. Speed just has magnitude. So for speed, I just care about how big is the number. I don't care about positive, negative, moving left or right. So to do this, we're just going to evaluate v of 3. So I would get 6 times 3 squared minus 30 times 3 plus 24. So this is 54 minus 90 plus 24, or negative 12, excuse me. So again, this would be measured in meters per second. So because the velocity is negative, that tells me we're moving left, but speed doesn't care about the direction. It just wants to know how fast is it moving. So speed in this case would just simply be 12 meters per second. So keep that in mind. Anytime that we're talking about speed, we're really just talking about velocity, but then we ignore the sign. All right, next one. Particle's position when the acceleration is 6 meters per second squared. So that one's tricky. So first I need to figure out where does a of t equal 6. So a of t, again, was equal to 12t minus 30. If I remember correctly, yep. So we need to set that guy equal to 6. So if I set that equal to 6, add 30, divide by 12, we get t equals 3. So now we need to go backwards and figure out what is x of 3 equal to. Well, we haven't found the position function yet. So to do that, we need to integrate the velocity function. So I'm going to integrate my 6t squared minus 30t plus 24 function with respect to time, or t. So that would give me 6t cubed over 3 minus 30t squared over 2 plus 24t plus c. But then remember that we were told that, excuse me, not s. Remember, for horizontal motion, we use x of t for position. We were told that the initial position that we started at was 0. So if your initial value is 0, then this constant is 0. So when I plug 0 in for all these t's, all these guys would drop out. So c would also equal 0, which essentially just means we don't have a c value. So let's go ahead and reduce this. My position function here would be 2t cubed minus 15t squared plus 24t. Now we can figure out what that value of x of 3 is equal to. Where is the particle after 3 seconds? T cubed is 27. 3 squared is 9. Plus 24 times 3. So we get 54 minus 135 plus 72, 126, or negative 9. So that means if we think about it on the x-axis, here's the origin where it starts. Now, we don't know exactly everything that occurs between t equals 0 and t equals 3, but I do know for sure that after 3 seconds, the particle is 9 units to the left of where it started. All right, next one. When is the particle changing directions? So remember that changing directions means that v, the velocity, equals 0, and it went from negative to positive or positive to negative around that value of time. So first we have to figure out the critical numbers. Again, this is just like finding relative extrema for position. So we're going to set our v of t equation, which was the 6t squared minus 30t plus 24. We're going to set that guy equal to 0. So I'm going to go ahead and pull out a GCF of 6 here. We'll make this easier for us. Similar numbers as earlier. So we end up, I can divide out by 6, but we end up with t minus 4 and t minus 1, or t equals 1 and 4. So those are our critical numbers. Now we need to actually check out the signs of them. So we're going to set up a first derivative chart. So this time we're not going to call it a derivative, we're going to call it velocity. But we can check between, whoops. This time we're not going to go to negative infinity because again we're starting at t equals 0. So we're going to go 0 to 1, 1 to 4, and then 4 to infinity. So we just want to make sure that it actually changes directions around those and doesn't just keep going in the same direction. So we know these made it 0, so I'm going to try 0.5, 2, and 5. If I plug 0.5 into here, we would get negative times a negative, so positive. So that means the particle is going to the right to begin with. After 1 second, it comes to a stop. And if I plug 2 in, I get negative times a positive. So it did change directions at t equals 1. Now we're going to the left. And then if I plug 5 in, I get positive, positive. So we did, in fact, change directions 2 times after 1 second and 4 seconds. All right, and the last one in this marathon video, I'm about ready for a nap, is asking, when is the particle furthest to the left? Okay, well, if we really think about it, we know that it starts at the origin, 0, 0. After 1 second, we are going to the right, and between 1 and 4 is the only time that we are actually moving to the left, because after that, we begin going to the right again. So the only time that this could be furthest to the left is by the end of the interval that it's moving to the left. Now that is if that position has surpassed the starting point of 0. So if it doesn't move past 0, so let's say that we stopped, we moved for that interval and we only made it this far, then the original would be the starting point. So in this case, we're going to check 3 things. Or another way of thinking about this is we have a given interval that we can test for an absolute minimum. So we can stop the interval at 4 because that's where we know we end going to the left. So we're going to test at 0, the critical number in it, 1, and then 4. So in this case, let's see. So at 0, we know we're at 0. Whoops, sorry, not velocity. We're going to go back to position. So this is, oh, actually, I'm sorry, this should be a t value. So when t equals 1 or 0, we know the position is 0. When t equals 1, now we can use our position equation up here. So that would give us 2 minus 15 plus 24, or 11. So think about that in terms of your visualization. After 1 second, we are 11 units to the right. And now we're going to start moving back to the left. So we need to figure out what t equals 4 produces. So that one's going to require some math. So 4 cubed is 64, or 128. Minus 15 times 4 squared is 16. That's 240. And then 24 times 4 is 96. So we get 224 minus 240, or negative 16. So that is a smaller position than 0. So our particle would be furthest to the left at t equals 4.